Over the last few videos, we've learned how to take the integral of x to the nth power, 1 over x, e to the x, e to the negative x, and a bunch of different trig functions. Now we need to build in some different properties so that we can piece them together in different ways. One of the first properties that we can learn is the additive and subtractive integral property. This allows us to have multiple terms in a single integral and break them up into little parts. So we'll take a look at some examples. We'll integrate some, do some definite integrals to show how the limits change things, and graphically show how the different parts do add up to the sum. What the additive integral property tells us is that if I have an integral of f of x plus g of x, I can break it up to an integral of f of x plus the separate integral of g of x. The subtractive property tells us basically the same thing. It says if there's an integral of f of x minus g of x, I could take that as an integral of f of x minus the integral of g of x. Now we can use any of the integral properties that we've determined already and piece it together in this way. We're going to start off by looking at a constant because that allows us to really easily see how the areas are added or subtracted from each other to really reinforce this property, right? The additive and subtractive property. Now we're going to use definite integrals because that gives us limits, and so then we can actually look at actual shaded areas. Of course, this property is true for any indefinite integral as well. When we look at the definite integrals, remember, because we apply some limits, we don't need to worry about the constant c out here that we apply for the indefinite integral. Now, if you're not convinced with it, keep it on, right? You can add the c term. Just remember, when you apply the limits, the upper and lower limits, you take it of the entire function. So that c value goes for the upper limit and it's subtracted again for the lower limit. So it's always going to drop out. So let's take a look at an example. So in our first example, we have 2 plus 5 as our function, right? So this could be seen as a total integral of 7. And we could also break it up as the integral of 2 separately as the integral of 5. So we can take the integral of this side here, and we're going to show that it will equal the integral of this side, and then we'll graphically show it. So the integral of a constant, remember, is just a constant times x. So this will give me 2x, and this will give me 5x. The total function will give me 7x. And so we got 2x plus 5x, and separately we have the upper and lower limits of 3 to 6. So I apply my upper limit here, upper limit of 6 minus the lower limit of 3. So 2 times 6 minus 3, which is 6. And then I do the same thing for 5x. I got 5 times upper limit 6, lower limit 3, 5 times 3, I got 15. So add them together, you get 21. The same thing if you integrated the total integral of 7, we get 7x. So you apply your upper and lower limits, you get 7 times 3, you get 21. Right? This makes sense. Graphically, what does this look like? Graphically, here I have my integral of 2x from 3 to 6, and here I have my integral of 5x from 3 to 6. So if I'm adding these two functions or these two integrals together, I'm just taking this area here and applying it up here. And that's what we get for the integral of 7. So clearly the additive property works for a constant, the integral of a constant. We can show the same thing for the subtractive property. So here I have 6 minus 4 as my integral. Our limits are 1 to 3 in this case. So this is 2x with lower limit of 1 and upper limit of 3. So 2 times 3 minus 1, or 2 times 2. This should give me 4. The area is 4. So I could break up my integral into integral of 6 and integral of 4. And let's see if we get the same area. So I get 6x here minus integral of 4x over here. And then apply my limits. So 6 times upper limit 3 minus lower limit 1 minus 4 times upper limit 3, lower limit 1. I get 12 minus 8. I do get 4 as we did expect, right? What does this look like graphically? Here's my integral of 6, and here's my integral of 4, and I subtract it, it will be the difference, should be this area up here, and that's what we get, right? So that's, if I grab this section and place it up here, I get my integral of 6. So clearly it works for a easy integral like the constant c. We're going to apply the same concepts to other integral properties that we've already developed in the past few videos, and hopefully graphically also be able to show you that this setup works. And now we apply the additive and subtractive properties to different kinds of functions. We're going to look at x to the nth power. We know that the integral of that is 1 over n plus 1 times x to the n plus 1. And let's take a look at our first example. So we have 250 plus x squared. We know that from the additive property that we can break this up into the integral of 250 plus the integral of x squared. So pause this video, see if you can take the integral of these individual components using the properties that we have here, and apply your limits. See if you get the same thing as what we have here. If you are able to, either through your computer or a graphing calculator, see if you can graph these, or even by hand, right? See if you can graph it and convince yourself. We're going to do it together here as well, but pause the video, see if you can solve for this, and then come back and watch the rest of this video. Okay, so hopefully you had a chance to try this problem. 250 is just a constant, so I can say 250x there. X squared is x to some power, so this is going to be 1 over 3x cubed, right? So I'll get 250x, 1/3 x cubed, and I apply my limits 30 to 50. So for 250x, I get 250 times the quantity 50, the upper limit, minus 30, the lower limit, plus 1/3 x cubed gives me 1/3 50 cubed, my upper limit, minus 30 cubed, the lower limit. Now I'm factoring out this constant in front, right? Here and here. You don't have to do it, obviously. You could write 250 times 50 minus 250 times 30. You could write 1/3 50 cubed minus 1/3 30 cubed. Obviously the same thing. We plug in our calculators, each individual part. We get each individual area, and we get the sum of the two, which is this total integral. So graphically, how does this get represented? So here's my constant 250 integral. Here's my x squared integral. So if I just add these together, I think it's easier to think about this as placing at the bottom and just bumping up my x squared graph by 250. And that's exactly what we get, right? So this section down here is basically this 250 area, and this section up here is basically the x squared, right? And you can see it from the 250 plus x squared functional graph, the line graph, as this shift off of the origin from the x squared term. Okay, so let's take a look at another example with a subtractive and additive component. So here we have the integral from -6 to -1, x minus 3 times x plus 4. That's the total function. Well, I can expand this. I get x squared plus x minus 3 times 4, I get minus 12. So I can break this up into 3 terms. Now, you can break this into 100 terms for all we care, right? The additive property works, the subtractive property works, no matter how many terms you get. So I have an x squared component, I have an x component, and I have a 12 component. This one's adding each other to each other. This one's subtracting from each other. All right, but the same principles apply. So pause this video, see if you can take the integral of each of these individual terms and what areas you get for each of them. All right, so the integral of x squared, right, n equals 2, so I'm going to get 1/3 x cubed, just like we had earlier. Integral of x, that's x to the n equals 1 power, so I get 1/2 x squared. 12 is just a constant, so I'm going to get 12x. So I get 1/3 x cubed, I get 1/2 x squared, and I have 12x. We apply our limits, 1/3, and we apply upper limit minus lower limit, right? So minus 1 cubed minus 6 or negative 6 cubed. Here I get 1/2 negative 1 squared minus negative 6 squared. Here we have minus 12 times negative 1 minus negative 6 or plus 6. And we plug these into our calculator and we get these individual areas, add them all together or subtract them, and we get our total area. So graphically, does this help us visualize what's going on here? Well, let's see, x squared, I have this side here. X, I have this side here. And my constant 12 that I'm going to subtract is this side here. So this side is going to subtract. So I'm basically shifting this x squared graph down. The x curve, this one's going to be hard to visually see it represented because it's such a small contribution compared to the other two terms. But at least the total, you can definitely see that the shift contribution. Remember, when we're below the x-axis, it's the area above the curve, like we show here, right? And this will be a negative area. This would be a positive area. So you can see that this area is larger than this area. So our total area is a negative value, okay? So we have not looked at exponentials, natural log result, or any of the trig functions. So that's what we're going to take a look at next. We can apply the additive and subtractive properties to other kinds of functions. Here we're going to apply it to exponential and trig functions. So here's an example of the total function that we can look at. This shows an example of something that has some sort of oscillation and then all of a sudden explodes. This could be something, this could be any kind of property, right? It could be temperature. There's some kind of thermal control, and all of a sudden you hit a breaking point and then you have an explosion or a fire that breaks out, and then you'll have a drastic increase. Or it could be something vibration based, right? There's oscillating vibrations, and then you hit a resonance frequency and then it explodes. Or it could be a pressure wave that's oscillating, or it could be any kind of property, right? So let's take a look at an example of this. This is an example of 10 sine x plus e to the x, right? You got my oscillation term right there, and I know e to the x behaves in this way. So this makes sense that this graph would be represented here. Now we can break up this graph into individual components, right? So I can have an integral of 10 sine x. I can leave this 10, the constant 10 in the integral, or pull it out like we discussed in the previous video, plus integral of e to the x. If you want to solve this, press pause and solve it. And I'm going to walk through the math of it and then graphically show this as well. So integral of sine of x is negative cosine x. So I'm going to get negative 10 cosine x. And integral of e to the x is just e to the x. So we take the integral, we get negative cosine x, we get e to the x. When we apply the limits 0 to pi, I get the negative 10 times cosine pi. Cosine pi, so pi is 180 degrees, so that's the negative x direction. So this will give me negative 1, which I see right here. Cosine at 0. Cosine 0 is going to give me positive 1 because that's the positive x-axis. So I get negative 1 minus plus positive 1, right? So negative 1 minus 1. For e to the x, I get e to the pi minus e to the 0th power, or just 1. Anything to power of 0 is equal to 1, right? So I get 20 for the sine integral term and 22.14 for the e to x term. So the total of that gives me 42.14. Now graphically, what does this represent? So the integral, the area under the 10 sine x curve is shown here. and the area under the EX curve is shown here. So we add them together, you see the combination of the sine part right here, and then the e to x growth piece plus the sine component right there. Okay, so same exact concept, different functions, so the individual components are different, but the principle is the same. All right, let's take a look at one last example. The last example, I just basically want to do the reverse of this. Maybe something is decaying quickly and then it has some kind of oscillating behavior. Could be a dampening for a mass spring system is turned on, right? We can control the dampening at different points with voltages, current and voltages for different systems, or with fluid flow. A lot of different things can have a behavior like this. Maybe something is triggered and it's the system is too hot. Let's cool it down. So you blow cold air over it initially, and then you want to slow down the cooling process afterwards. So this type of system shows up a lot as well. A lot of different ways we can get the system to show up. One way could be a 1 over x type of graph, and then add or subtract a oscillating term, in this case subtracting a cosine term. So I get 4 over x and 5 cosine x. Right? So we're going to subtract these two functions. We're going to apply the limits pi over 4 to pi. So again, press pause, try to solve this one on your own, and then come back and see if you match what we get. So 4 over x, this is just basically 4 times 1 over x, right? 1 over x, I'm forcing in here so that I can see the natural log of function show up. So this is going to be 4 natural log x. 5 cosine x, this is 5 times the integral cosine x, right? So cosine x, over here we get sine x, right? So we integrate, we have 4 natural log x minus 5 sine x with my pi over 4 to pi limits. So for my natural log x, I get 4 natural log pi minus natural log pi over 4 minus 5 sine of pi. Remember, pi is 180 degrees, so y value is equal to 0 on the unit circle. So that's why they have 0 there. Minus sine pi over 4. Remember, pi over 4 is just 45 degrees. So I got my isosceles triangle, so that's going to be 1 over root 2. And I get my individual area for my 4 over x integral, and then I get my individual area, negative 3.5, for my 5 cosine x term. Right? So I'm going to subtract that negative value. And then I get a positive 9.1. So this is from pi over 4 to pi. And so let's see, there's pi over 4, and there's pi. And so it makes sense, at least from the signage, that I'm going to get a positive total area. So let's look at each term graphically. So here I have my 4 over x graph, and then the area that's resulting from that, 5.6. And then here's my 5 cosine x graph, and we can see that the area under the curve that's shaded is larger than the area above the curve here. So this gives me a negative value as expected here. And then when I piece them together, we can see the combination of these two graphs, right? The initial part, this 4 over x graph dominates. And then afterwards, the results or the contribution of the cosine term is observed here. Now recognize it's a negative cosine, so this is basically flipped and then added together. That's why this bumps up here. And we do see that all of it is above the x-axis, so the area is positive. So additive and subtractive property is extremely useful and used a lot. We will need to use different tools if functions are multiplied to each other. And so we'll start looking at that next.